So, all right. So with that, we'll go ahead and dive back into our lecture for today, which is the second lecture on practical I/O and just kind of capturing some non-ideal parameters and aspects related to digital circuitry and logic gates, sequential circuits in particular. We're adding in some other functionalities that we need to keep in mind for real systems. So we're going to start with the idea of Schmidt triggers and practical I/O. Chapter 11 in your book, if you're following along. Oops. So first, introduction of the Schmidt trigger. You may have run into this before, possibly not. But essentially, if you look at a regular inverter and you send a noisy signal through a regular inverter, if the noise is kind of making your signal go up and down, maybe you have some waveforms interacting with it, every time you cross above or below the threshold of an inverter, your output signal is going to flip. And so what noisy signals will do to a standard inverter is give you kind of these spikes high and low. You might get some, what looks kind of like switch bouncing, but that's just from the crossing above and below if you have noise in your signal as you cross the threshold of the inverter. What a Schmidt inverter or Schmidt trigger or Schmidt inverter is an inverter with a bit of a gap in its going high and going low threshold. Meaning it will turn high at a lower, or sorry, you'll cross where you go high to low, invert from low to high or high to low at a lower threshold, but it doesn't actually turn back until a higher threshold. What that means is in this intermediate region, you're not flipping back and forth just at one threshold, but even if you dip below your positive going threshold, you don't reach clear down to that negative threshold because it's separated. It's not just one line that you're jumping back and forth across. They're separated by a space where the change doesn't occur. So there's this positive going threshold a little higher, this negative threshold a little lower. So if your signal is a bit noisy, you're not getting a rapid toggle back and forth situation. And so Schmidt triggers are useful to speed up transitions, reach the next stable state quicker because you don't have any back and forth toggling. And the definition to introduce here, if you haven't seen it before, is the idea of hysteresis. So that's the behavior of a system as it goes forward in one direction and then back the other, essentially. And it's used in a lot of different realms. Our MET colleagues talk about hysteresis when they look at bending plastic one way and then back the other way and see what that behavior looks like on a stress strain curve. For us, we have a use of hysteresis here when we talk about moving across an inverter in one direction and then another direction. So going low and then going back high, for example. And so hysteresis really is looking forward and back on this transfer function, which is a term, if you haven't used it yet, you will in some future classes. But you're basically looking at the input on the x-axis versus the output on the y-axis. So if your input is low, your output is high. If your input is high, the output is low. And so it's kind of an odd shape to wrap your head around, but it's just the input on the x, output on the y. This is for an inverter. And if your inverter is a standard inverter, these lines would be the same. And so at a certain level, it goes low to high or high to low. But for the Schmidt trigger, at a certain low point, we have our high going threshold. And then here, you need a little bit higher to have your low going output threshold. And by separating those two, there's a tolerance for noise, so we don't get a rapid jittering. So Schmidt triggers are a way to clean up signals a bit around potentially noisy signals. And speed up transfer a bit. Rather than looking at the transfer function, if you're just looking at V out over time, if you were given a triangular wave, you can experimentally map out what those thresholds are just by looking at when your device transitions, either at its high point, which would trigger the output to be inverted, or low, or its low point, which would invert the output to high, but it shifted a little bit. It wouldn't be centered around the triangle. It shifted a little bit because of that noise threshold, noise absorbing threshold on our Schmidt trigger. The symbol looks like this, and so you'll run into this on schematics where you have this symbol, which is the transfer function of it, is the symbol that highlights what's special about this particular device. And so you may run into that on a schematic level diagram. So that's just one of a few items we're going to talk about. We're going to highlight again the idea of switch bouncing. We've talked about this in previous courses in a few different ways. Essentially, a switch is a mechanical device that has potentially some spring constant as contacts collide. At that collision point, you can have bouncing between contacts, and electrically, that's going to look like a switch bouncing open and closed. And so you can see those bounces happening here. And we talked about in previous courses in our 179 a bit about eliminating switch bounce and ways of doing that. We have software-based methods such as when you get your first bounce, just delay a little bit before you capture the state and use it for something else. You have physical mechanisms of debouncing, like putting a capacitor over your contact to ground, and that's going to absorb some of that bouncing. The capacitor can't change voltage instantly because of its physical nature, and so that can eliminate some of those bounces as well. This first figure here is just illustrating switch bounce. And if you had a bouncing switch on a toggling flip-flop, like say you were counting, like we saw in our previous labs, we had to debounce in ICE Studio. Otherwise, this count would go up multiple times. However many bounces would be how many numbers it toggled or incremented. So one method of debouncing is using a capacitor along with a Schmidt trigger. Capacitor, again, you know from your Physics 2 class, isn't going to be able to change voltage immediately. It has this, energy reservoir, and so when the switch switches, the result will not be instantaneous, but you do get some ripple. The Schmidt trigger can absorb some of that ripple off of that capacitor as well. So during the bouncing operation, the capacitor doesn't let it energy level, the voltage level bounce the whole way. The Schmidt trigger can eliminate some of that noise at the transition and give you a smoother output signal. So here's one hardware-based debouncing method using a capacitor, which we did talk about before a bit, and then a Schmidt trigger as well to improve the performance of that by changing the going high and going low thresholds and giving a gap there. Here's a second debouncing mechanism made purely out of digital logic. So I would say this is not quite as common to see this type of logical debouncing, but it is a way of doing it. Essentially, we have a two-position switch going between A and B. So if you try to switch to A, it's going to lock in the output to A, and even if you're bouncing against A, you're not changing the state. And then your switch could go the other way to B. When you hit B, because of the logic looping back on itself, it's essentially a set reset flip-flop that's going to set B. And even if your switch is bouncing against B, it doesn't change the state. So you eliminate bouncing by just setting one direction or the other. So there's a mechanical one way or the other element there, and then a logic, latch system to just hold that state. So we can use logic along with a slightly more mechanically complex switch. So it's got two outputs, A and B, to also debounce. Here's a D flip-flop method, basically showing the same kind of thing where you have the A or B and using a flip-flop to just capture that. And then the bouncing is essentially just ignored because we have two different contacts which you could be bouncing against. So you just latch whatever's being activated and the bouncing is ignored in this type of system. Next item, just talking about pull-up resistors. We've used these all the time for various purposes. You In your 179 course, for example, we talked about activating our pull-up resistors. We had them available internally, on the microcontrollers we were using. Essentially, pull-up resistors eliminate floating contacts by pulling them high to your power, whatever your power level that you're pulling up to is, which is 5 volts on our mega systems. But activating pull-up resistors prevents or eliminates those floating contacts. And floating contacts can build up charge, and they're not connected anywhere. So we can't say with 100% certainty what state they're in. And so for digital logic, as you already know, we want to know the state of everything in a fixed manner. So pull-up resistors allow us to do that. We'll look in a minute on how we can use pull-up resistors to interface between devices, although we talked about that last time as well. If we have open collector style devices, pull-up resistors can allow us to go from one voltage level to another by using a pull-up resistor along with an open collector style device, which is a device that is either grounded or floating, and then we can adjust the floating side with the pull-up resistor. There are pulled down resistor configurations as well. I would say just in my own experience, I come across that a lot less. We tend to have pull up activation with active going to ground when we hit the button, for example, and then it stays in its high state when we're not hitting the button. So when we're driving LEDs, we have limiting resistors associated with those devices as well. And that ties into the syncing and sourcing capability of our logic. For anyone that had your Arduino Mega in hand and you wanted to run a motor off of it, so you hook it straight into the pin and then the motor or the pin goes out, or you're running a speaker straight off of a pin trying to make a tone, you'll burn out those pins rather quickly. They can usually handle an LED, especially if you have a current limiting resistor on there. But as we've kind of discussed, and you'll see through the course of your homework 6, and we talked about yesterday, digital electronics and logic gates don't sync or source a lot of current. So beyond maybe an LED, those inputs are not intended for running devices. And so we interface with transistors for a lot of things. To drive elements like motors or other high power items. But this is just a reminder that a limiting resistor on an LED is always good practice to include that current limiting resistor. Okay, so let's move on to our timing parameters a bit. This is going to be mostly in relation to flip-flops, so D flip-flops, SR flip-flops, and even JK. But we'll be kind of in the weeds with SR flip-flops a bit for some of these. The first we want to mention is the idea of a race condition. You can't really see on the slide, but these are purple versus black text, so kind of highlight the definitions that are important when you look at those on your own device. A race condition, meaning the inputs are changing at the same time as a clock edge, which means changing input at the same time of a clock edge, we are not able to determine for certain when that edge strikes if it's going to take the previous value or the next value, because we had a change right at the clock edge. So that's referred to as a race condition. Internally, the electrons are racing from point A to point B. The device is racing to switch, but we don't know what that setup actually is. For certain, at least not according to the manufacturer's data sheet. So yeah, race condition changing at the same time as an active clock edge. Active edge could be active high or active low. We're just saying an active edge. And so to prevent that race condition, we have what's known as the setup time. How far back do you need to set your inputs in order to determine or know for sure what those levels are going to be? So we have amount of setup time, meaning have your J and K or your S and R in place this much before you're looking for them to be utilized. And we have setup conditions that'll be given in a manufacturer's data sheet. They'll give you a setup time that is recommended for your system. So how much earlier do your inputs need to be in place before you try and use them? And the output is determined for sure. So again, setup time is to avoid race conditions. We have a hold time, how long the input levels must be held beyond the active clock edge. So we need to have a setup time for setting our inputs before an active edge, for example, and then an amount of hold time after, because there still could be physical charging and discharging at the nanosecond or even smaller scales at and around a clock edge that are drawing from inputs as part of the functionality of a chip. So there's an amount of hold time after a clock edge that you don't want to change anything too quick. Otherwise, it could affect the calculation of electrically of what happens at the output. So setup time before an edge, hold time after an edge. And then delay from input to output, we've already talked about propagation delay previously, especially in terms of our flip-flops connected one to the next if we had a ripple counter, for example. So there's an amount of propagation delay between an activated input before it becomes clear on the output, or before that effect has made it to the output. So usually there's separate propagation delays given in a manufacturer's data sheet for propagation high to low, or you'd see a subscript PHL, so propagation high to low, or propagation low to high, T, lowercase t, and then subscript PLH. So different propagation delays for which way the output is changing, but in both cases, there's a little bit of delay between inputs to outputs. And we've highlighted that already, but just to refresh. So all of these items and more are in manufacturer data sheets. We've seen some snippets of those as part of the tests, and occasionally a tiny piece in the labs. But if you ever have a device that you are operating, maybe running with a microcontroller, for example, at high frequencies, you may need to reference some of these items to make sure you're working with it properly. And there are other items like maximum frequency that you can run a device. The clock pulse sizes. So if you require a certain amount of high time or a certain amount of low time to run a device, you might have clock pulse width sizes given, and the width of set of reset pulses. So if you're giving an asynchronous input to a flip-flop, how long does that asynchronous input need to be? You know from your calculus class, a theoretical impulse is like 1 instant. It needs to be longer than that for a real device. And so manufacturers have found out how wide or how long must the pulse be to activate an asynchronous input, for example. And then we mentioned with the SR flip-flop, a metastable state output voltage is an invalid or unknown level. We aspire for all our ICs to provide exact delays, and so we can time out and know the state of all inputs and outputs over time in a very fixed fashion. We look to avoid these unknown or metastable states if possible. Or if we do have them, they need to be clearly marked on our timing diagram, so we know we can't get a clean capture of that waveform at that instant in time. All right, so we've been talking about counters in a few different varieties. We wanted to introduce just a circuit for automatic reset that powers up circuits to start at 0. This has been a default case for the counters we've made in iStudio. They just start at 0, but for physical switches, we need to electrically set that up, and a capacitor and resistor on your power supply will do that. Initially, your power supply, is off, and then when you switch your power supply on, this capacitor is not yet charged, So we are giving an active high to both our power supply, but also to R1 and R2, which are a reset for a chip. Because they're active low, and no current is being dropped over the, or sorry, all the current is being dropped over this resistor because this capacitor is not charged. This is essentially ground when you first flip on your power supply. So both resets are activated. Then as that capacitor charges, the resets will no longer be grounded as this charges up to your power supply. So you get an initial active low off of this setup, and then once that capacitor charges up, you're now holding your resets high. And what that does is you just reset your system as soon as it powers on, and then you're no longer, hitting the asynchronous reset once that capacitor charges up. So that's just a capacitor resistor setup to allow you to start your counters at 0 at a known value. If you flipped on your Arduino Mega, all of the counters on that system start at 0. So they likely have some circuitry that ensures that is the case. You don't want counters that start at, a bunch of random numbers. There it adds a lot of unknown complexity to how you need to code and interact with them. Okay, let's talk a bit about sensors. We historically, and I say in past years, have not focused on sensors too specifically. So we've added a little bit of modules, sprinkled them in here and there, just because casually you all tend to know the idea of sensors, but we wanted to make sure that's written down somewhere if you need to lean on a reference for whatever reason. So just the first idea is, what are sensors? It's just a device that produces an output from some input that you're trying to measure. And this quantity you're trying to measure could be pretty much anything that has a unit. So heat or sound level, light level, distance, some sort of chemical property. But you can measure anything that you have physical access to and can find some sort of mechanism to convert that into an electrical signal. The part that does the conversion is the sensor, or called a transducer. So these are what translate that physical quantity into something electrical we can work with, the transducer, as part of that sensor. And the stimulus, as I already mentioned, can be all kinds of stuff. There are sensors for, any quantity that we could want. There's usually some physical, electromechanical mechanism to capture it. So a lot of those examples are here, whether it's fluid concentrations in a water treatment system, keep adding chlorine till it reaches a certain level. You can measure that level by looking at conductivity or maybe optically looking at it in some way. There are a lot of electrical mechanisms and magnetic. There's, absorption and heat related items. Mechanical stresses and strains are going to cause changes in resistances. So if you can find a physical property that you can convert to electrical, you can usually make that into some kind of sensor. You may or may not have seen these mentioned in your physics classes, but there are a lot of physical principles at work behind sensing systems. And it's a very, a field you can focus into for very specific types of sensing and applications. But even just in your cell phone or in your car, you have dozens of sensors looking at all kinds of different parts of it. It's why the technician can plug into your car, see the status of points all around the engine and the pressures of all the tires and so on and so forth. It's just embedded sensor digital systems all over the place, capturing a lot of different data. And so our sort of automated systems require sensing in some form. And choice of sensors tends to be, you need a sensor that is accurate for your application, or as accurate as your application requires. And so you'll maybe get in a little more depth in this later. So if you're sensing pressure in your car tire, for example, you may only have a certain number of decimal digits that your car captures or displays to the driver. Well, we don't need the most expensive sensor out to, 300 decimal points of accuracy. Maybe something a little less is cheaper, but meets the needs of the application. And so there's a balancing act, as with most things in engineering related fields, between how much it costs to make, sourcing materials for more expensive sensors, things like that, and the error and reliability of those sensors. It's very application specific. So like many things, choosing a sensor is based on the application you're trying to target. And they're all over the place, capturing all kinds of phenomena. We already mentioned that. Some just types of sensors that illustrate some of the physical effects. Here's a bimetallic strip, and you might have two pieces of material that expand at different rates. So as the temperature changes, this metallic strip would kind of physically curve up or curve down. It also has some electrical changes as the strain between those materials change. So you're converting mechanical responses into electrical elements. You have, resistance that changes as a function of temperature for most materials. Some have more change than others, and so there are more appropriate materials for temperature sensing. But essentially, you get a resistance change over changing temperature out of a lot of these types of sensors. And so that, again, gives you a quantity you can interact with, run a current, measure a voltage level, and you can see those changes, map them over time. Accelerometers are based on moving masses or bending cantilever beams. So you have some piezoelectric effect, meaning as the stress and strain changes, the resistance changes, and so you have a measurable quantity in physical maneuvering or physical movement of a physical, cantilever beam, for example, or a gyroscope would be a more complex geometry. But as you turn your cell phone to the side, it knows to flip the screen because there's acceleration applied. And you can measure those physical happenings electrically and make choices based on that. Light sensors can use a lot of the internal structure of diode or LEDs, but the reverse operation of diode or LEDs in particular also is possible. If you have light hitting a diode system, it can be constructed so that you can capture current being pushed on that junction rather than emitting the light. You can measure the changes when light's coming in. So you can capture light in a lot of ways. You can capture magnetic fields because it interacts with electric fields and voltage potential differences. So again, all our traditional voltage, current, Ohm's law can really be used to capture things off of physical systems in the idea of sensors. Ultrasonic, more of a software-based mechanism. You may have interacted with these in previous classes, but sending a sound wave and it bounces back, hits a diaphragm, and you measure the time distance, and knowing the speed of sound, you're now measuring distances. Photo gates, you might have a laser pointing from one side to a receiver at the other, and if you break that beam, you can see that that has happened. So again, just getting creative with the physical setup to create electrical signals. Gas sensors can be captured optically or electrically. Running current may have different resistances or conductivity based on chemical properties. That's kind of where we wanted to leave it with sensors. We, in this package, just introduced a bunch of different types. The application of those will be sprinkled in over the remainder of your career here in various forms. That's where we're going to end it today at the end of our practical I/O section.